Hello everyone and welcome back to the Neural Networks Explained series, episode 11. Today we're going to code a neural network from scratch using only Python and NumPy, and it's going to be used on the simple XOR problem. You can adapt our model, our little toy model, to pretty much any input you want, but for now we're sticking with XOR because it's an easy problem, and we're going to be using Sigmoid or ReLU activation functions along with mean squared error. So if you don't know what these terms mean, check out my previous videos and come back here. Otherwise, you can still follow along and try to understand because I think it should be okay when it's with code. So first thing first, let's get into a JupyterLab notebook and I'll be showing you how everything works. So the first thing we're going to do is just verify we have NumPy installed. So if you just do import NumPy as np and np.__version, and you run it, you should see something like 1.21.4 or whatever NumPy version you're on. It doesn't really matter what NumPy version you're on because it should be the same for what we're going to use today. So the first thing we're going to write is the code for the dense layer, and it's going to look like this. So here I create a class called dense layer, and when you initialize the class, you have to pass in the number of input nodes and the number of output nodes, and it's just going to store that. And then it's going to store a set of weight. So self.weight is equal to np.random.randn self.output nodes times self.input nodes .reshape self.output nodes self.input nodes. So this is just creating a matrix, so a grid with here it's the number of output nodes and here it's the number of input nodes. And once you multiply the weight by the input, it's going to generate your new sequence of prediction. But it's not done yet. Now you have to add in the bias and activate it, which is what we're going to do right now. To add a bias, I can just create self.bias is equal to np.random.randn, and what's the shape going to be like? It's going to be the shape of the output nodes because we're adding it to the output. So self.output nodes, and we're going to leave it like this. So we're randomly initializing each parameter, and we're going to fine tune them. We're going to adapt them with gradient descent so it becomes the most optimal. So we have our matrix multiplication self.weight at x. So if I just run this, you see I did get some output, so the shape is correct. Now I have to add in the bias. So I do plus self.bias, and let's see if this breaks any code. So once I run this and I run this, nope, it doesn't break anything and my bias does indeed work. So moving on, we're going to add in the activation function. So we're going to add in the two activation functions, Sigmoid and ReLU. So to do that, let's just do class ReLU activation, define init, and it doesn't need anything to initialize. And then we're going to do class Sigmoid activation, define init, and it doesn't need anything as well. So I actually don't really even need the init here. All I need to do is just pass in some methods. So let's just keep forward. It's going to take self and x, and here same thing, define forward. It's going to take self and x, and it's going to return some stuff. So if you remember ReLU, it's going to be 0 if it's smaller than 0, and it's going to be itself if it's bigger. So I can implement that by just doing return np.max x and 0, because once it's smaller than 0, for example like -5, the maximum between -5 and 0 is going to be 0, so it's going to be, for all negative numbers, it's going to be 0. And if you look at the positive numbers, for example 10, the maximum between 0 and 10 is going to be 10, so this is indeed the ReLU activation function. And for the sigmoid, if you remember, it's 1 over 1 plus e to the minus x, and it gives this sort of squished like S curve, which is just going to be like a smooth brain activation, something like that. So what you can do to implement it is just do return 1 over 1 plus the exponential np.exp minus x. So this is going to be the forward, and well, that's it. So let's try it now, and I'm going to do Sigmoid activation is equal to Sigmoid activation, and then I'm going to try to activate it. So Sigmoid activation dot forward, let's let's forward this np.array. Wait, let's just take these numbers. So sample input, and let's see if we get an output. So it doesn't work, and let's try to fix that. So replace that with a capital X, and we're good to go, I believe. And bam, you see we get our sigmoid input. So just for a sanity check, I'm going to pass in instead some very large numbers, and I'm going to hope it's going to become 1, and some very small negative numbers, and I'm going to hope it's -1. No, it's going to hope to be 0, I mean. So let's put in 1, yeah, this large number and this large number but negative. So we should get something like 1 and 0. So as you can see, we do get 1 and 0, and now the last thing we need is just to pass in 0 itself, and I hope we get something like 0.5. So yeah, we did get 0.5, so our implementation of ReLU does work. So now let's try to switch it to ReLU. So ReLU activation is equal to ReLU activation. And I'm just going to say ReLU activation dot forward np.array. Let's pass in a negative number like -25 and a 0 and 125. So you can see from the input that it's not working. We did something wrong with it, and I think we just took the maximum from everything. So instead, what I need to do is I have to do np.max. Wait, I'll be back. Alright, I found the answer. And instead of just doing the maximum between 0 and x, let's try to maximum. Then let's do it again. And as you can see, now it works. So I just used the wrong method name. You can do you should do np.maximum instead of np.max. The next thing to do is implement our loss. So we're going to use the mean squared error loss, which is just going to be the mean of the squared error. So I'll have a class called MSE loss defined forward, and it's going to accept the y true and y pred. So our predictions and the true targets, and it's going to calculate the error in that. All we need to do is just return np.mean between what? Between y true minus y pred, and that whole thing we square it. So we squared it, and bam, this should be what we're looking for. So let's create it. MSE is equal to MSE loss, and what I can do right now is just do MSE dot forward. Let's pass in np.array 11, np.array 11, and this should be 0. So it doesn't work. So I think the reason why is because I forgot to pass in the self over here, which is just going to act in as like, you know, how to access the properties in the class, and you're forced to put that in every single class methods. So now it works. So when you put in identical numbers, the loss is 0, which is good, because if you predict the same output as what you're expected to do, you're really good, so you have a loss of 0. Let's put this one a bit different, so 0.99, and I should get a small number. So here I have 5 to the times 10 to the minus 0.5. So this is really good. Let's get a bit further away. Okay, and as you can see, it is increasing. So if I put in, for example, 2, yeah, so the mean squared error loss is indeed working. So now that we have all of these components, we can start building a full-fledged neural network, and let's do that right away. So we're going to have our class. Neural network, and it's going to basically accept a list of layers, and that's it. So define init self layers, and it's going to accept list of layers as we said before. So we're going to do self.layers is equal to layers. It's also going to accept a loss. So self.loss is equal to loss. So once we have that in, we have to call our forward method. So define forward, it's going to take in self, and then it's going to take in x. So what I'm going to do now is just going to go through over each layer and just apply operation and continue till the output. So I can do for layer in layers, I can say current input is equal to x. I can just say for layer in layers, layer.forward current input, and say that current input is equal to this. And then finally, I just return the current input, And that's it. Easy peasy. Alright, let's continue. And now we're just going to look at all the code here, and I'm just going to modify a bit of the code to prepare us for the next step, which is going to be backpropagation. So for now, we're just going to have to make sure that for every input we can keep track of what was passed in or out. So here, what I'm going to do is for the dense layer, I'm going to have something called self.gradient is equal to none, and self.input is equal to none, just to have them initialized but to nothing. And then once we get them here to forward, what I can do is that we're going to pass in self.input. Well, it was just equal to x. And I'm also going to start running something called backward. So define backward self, and I'm going to have the incoming gradient from the opposite side, and I'm going to call that delta. And then all I can do is just write pass, and we're going to continue. So this is just going to accept the gradient coming out from these outer layers over there, and we're going to take this gradient and matrix multiply it or do whatever fancy stuff with it to get how much change should we apply to our own weights so that it learns. Now we have to do the same thing for the rest. So for ReLU, I have to keep track of what was the input. So here I can just do self.input is equal to x. And I can pass in the init method self, and that's it. And I can just do self.input is equal to none, self.grad equal to none. Are you putting grad or input? Let's put gradient. Self.gradient is equal to none. And for Sigmoid, we also have the same thing. So it's a bit of a code repetition, but don't worry, this is okay. So self.input equal to none, self.gradient is equal to none. And here I'm just doing self.input is equal to x. And for the Sigmoid activation, we're going to do something a bit cheaty, which is just that for the Sigmoid, it's easier to use the output to calculate the gradient instead of the input. So I'm also going to add in another parameter called self.output is equal to none, and here I'm going to have self.output is equal to this, return self.output. So technically I really don't need the self.input, so I can comment that out because it's more efficient from the Sigmoid point of view to use the output to calculate the gradient instead of like ReLU, where you can just use the input instead. Alright, time to write some gradients. So first we're going to start with the easiest one, which is just ReLU. So for ReLU, if you think about it, well, how it works is that, well, you have 0 and then you have itself. So if you look at the slope, which is a derivative, it's going to be, well, here it's going to be 0 and here it's going to be 1. So that's it. So I'm going to have something called define backward. It's going to take in self as always, and it's going to take in the incoming gradient, which is just delta. I'll just call it delta. And now all I need to do is just, well, calculate what I need to add. So what I need to do is I take a look at input, and I say if it's smaller than 0, it's 0, and if it's bigger than 0, it's 1. Okay, I'm not sure if this is an efficient method, so let's try this first. I'm going to create a blank slate of zeros. So I'm going to have ReLU gradient is equal to np.zeros, like, and then this is zeros like, and I pass in what, well, the thing looks like, so delta. And then what I'm going to do now is just, well, ReLU gradient. Perhaps I should do self.input, and then I do ReLU gradient is equal where self.input is bigger than 0, it's equal to 1, and I just return the ReLU gradient. So it's going to look like this: return ReLU gradient times delta, and that's it. So this is going to do a Hadamard product, or just an element-wise product between the ReLU activations, gradients, along with the incoming gradient from the outer side. And then once you multiply them together, well, then this is the gradient you can feed into the previous layers. So now with this gradient, you can use it to feed into the previous layers, like the dense layers or other activation functions, and then they will at their turn learn. Let's do the same thing for Sigmoid as well as the dense layer. So let's do Sigmoid first because it's easiest. I'm leaving the hardest at last. So it's going to be define backward, self delta. And what I'm going to do now is that, well, you can calculate the derivative of the sigmoid by doing self.output times 1 minus self.output. So this is going to be just d sigmoid, and with this I'm going to return d sigmoid times delta. So just to be consistent here, I'll call this d ReLU, and I'll have d ReLU gradient, d ReLU like this, and then d ReLU times delta. D for, like, derivative, differential, whatever. So it looks like this. Sigmoid activation return d sigmoid times delta. This is the derivative of the sigmoid activation function, and then once you multiply it with the delta, this is just going to apply the chain rule, so you can just continue backwards. So I know this is really advanced mathematically, but if you just want to follow along with the code, that's fine. Otherwise, check out my video, as I said before, on the previous videos on neural networks explained. We're now ready to do the same on, well, the dense layer. So how this is going to work is that instead we have the delta, and we're going to have to find three things. We have to find the gradient for the weights, the gradient for the biases, and the gradient for the inputs. So the gradient for the weights is going to be applied on the weights itself, and it's going to be what we need to change it by so that it learns. The gradients on the bias is the same thing, but for the bias, so it's the values we need to subtract or add, depending on how you want to view it, to the bias to make it learn better. And finally, we have the gradient with respect to the input x, and this is going to be used to pass in for the past layers, which is in front of that. So the first thing I'm going to write is the gradient for the weight. So I noticed that this notation here is a bit cumbersome, so instead I'm just going to do self.gradient weight is equal to, none, and self.gradient bias is also equal to none. Finally, here I'm going to have the backward. So what I can do here is that I'm going to first calculate the gradient for the weight, then for the bias, and then for the input. So the gradient for the weight is going to be, well, it's, that the weight is, here it's the number of output nodes, and here it's the number of input nodes. So our dimension, our matrix dimension, has to match that. And the way we're going to do that is, well, what has the shape of the output node? Well, delta has the shape of output node. So it's going to be delta matrix multiplied by something that has the dimension of input nodes on the top. And this is going to be, well, the transpose of the self.input. So delta at self.input.t, and this is going to be dw. So the change I apply to the weights. So I'm going to call that self.gradient weight is equal to this, and for the bias it's going to be similar. So self.gradient bias, well, it's literally just delta itself. You don't even need to multiply by anything, it's just delta itself. And if you don't believe me, check out my previous videos on when I differentiate those rules. So self.gradient bias is just equal to delta itself. And finally, I have self.gradient input. So self.gradient input, well, and I'll just make dx. dx, well, the gradient with respect to the input, this has a shape of the number of input nodes. So what I have is that I have, well, the output nodes, I have something in the shape of the output nodes, which is the incoming gradient from the further layers over there. I have the weight. So I have to find a way to combine them together to get an output of input nodes. And the way I'm going to do that is that first, I think I need to... Okay, I found it. So basically, we want to get something that is of shape input nodes, right? Because the gradient of something with respect to something is going to have the same shape of that something. So if I'm doing the gradient with respect to the input, it has to have the same shape of the input, which is just a column with input nodes number of elements. So I have at my disposal the incoming gradient from the further layers, which is of shape output nodes, and I have a matrix, the weight, which is of shape output nodes by input nodes. So what I'm going to do is I'm going to transpose the gradient weight. So instead of being output nodes by input nodes, it's going to be input nodes by output nodes, and finally I'm going to multiply that with the output gradient, well, so the incoming gradient from the further side. So it's a bit convoluted, but if you look at the code, you'll see, wow, it's just this. So it's going to be, I take the transpose of the weight, so self.weight.t, and I matrix multiply it with the incoming gradient, delta, and that's it. And then I just return it. And yep, that's literally it. Now all of this is done. The last step is creating our optimizer and finishing the neural network class. So we're going to create an optimizer, and it's going to be like the simplest one you can possibly imagine. It's going to be just SGD, which stands for stochastic gradient descent. And it sounds a fancy term, but it's literally just you take the gradient and you subtract it, but you make sure to scale the gradient by a little bit to not make it like woo woo woo. So just there's a little change to the weights, to the biases, or to whatever thing you have to change, and then that's it. So class SGD Optimizer defined init is going to take in one parameter, which is the learning rate, self.lr, which is just float, and then self.lr equal lr, and I'm going to have something called apply. So define apply is going to take in, well, the vector, let's call it vector, and the gradient as vector, so let's call it d vector, and then I'm just going to apply it and return, well, what's the thing I should change it by. So it's going to be return vector minus d vector times self.lr, and you're done. That's literally a SGD optimizer done. So we have our SGD optimizer, we have everything, and now it's time to do this. Now we have to also have our apply function here. So define apply grad, and no, I'm just going to call it apply, and then it's going to take in self, it's going to take in optimizer, and it's just going to apply, well, the gradients. So it's going to look a bit like this. So I'm gonna have self.gradient weight is equal to opt.apply, and I'm going to pass in, well, the weight, so self.weight, and its gradient, so self.gradient weight. And I also have, oops, sorry, big typo, self.weight, I mean. And then now we have self.bias is equal to opt.apply, self.bias, self.gradient, bias, and you're done. So you have apply, backward, forward, and you have our SGD optimizer over here, our dense layer, and we have everything. Our ReLU and Sigmoid don't even need to be changed. All they do is just pass backward the gradient because they don't have any parameters to it, right? It's just activate, it's just a mathematical formula you plug in and you plug out. There's nothing to change, nothing to learn from. Alright, I made some fixes to the code to make sure that it works. So the first fix I applied was for the dense layer. So here, instead of just using like racial multiplication with transpose, what I did was that I explicitly said what shape it should be to keep my sanity intact. So we know that to generate the gradient for the weight, we have to have something that is of shape output nodes, matrix multiplied with something that is of shape input nodes but that is a row. So I did that in NumPy. So I have the delta that I reshaped to be self.output nodes by 1, which is going to be something like this. And then I have the input, which is going to be 1 self.input. So it's going to be like this. The transpose doesn't work because if you just have a one-dimensional vector, if you do the transpose of it, it gives the same thing. So you have to explicitly reshape it to make sure that it works. So now it works for me, and well, that's all I need to do. So if I show a demo of it, you see I have the dense layer forwarded, that's fine. And if I backwards it, it also works. And now you have the ReLU activation, which I also debug. So here you see I pass in the ReLU activation, and bam, it gives me numbers. And if I do the other thing, if I pass in the Sigmoid activation here, which was what it was originally, you see that I get, you know, numbers that work as well. Now it's time to add in the backward method to the MSE loss. So let's do that right away. So if you did a bit of calculus, define backward self, and what we're going to pass in is, well, the same thing, y true and y pred, and we're going to calculate, well, the gradient from that. So y true, y pred, and I'm going to return the gradient with respect to the y pred. So this is just going to be 2 times. Now, okay, I'll be a bit lazy. So here, I'm going to pass in a 0.5, and here I don't need to put it 2 times. And then here I'm just going to say it's going to be, well, the error term. So this is going to become ypred minus ytrue. So I return this, and return ypred minus ytrue is going to be the true gradient for pred. Because if you look at this, this is something squared, and once you apply the power rule to it, the 2 becomes in front of it, so it becomes 2 times ytrue minus ypred. But don't forget the chain rule. We have to again differentiate with respect to ypred. So since it's minus ypred, we put in a minus in front, so it becomes minus 2 times ytrue minus ypred. And since we have a 0.5, this becomes minus parenthesis ytrue minus ypred, which just becomes ypred minus ytrue. Trust me, the maths work. So this is good. And now let's do a simple sanity check again. So I do MSE equal MSE loss, and I do MSE.backward. I pass in ytrue and ypred. So let's say np.array 1 2, np.array 2 0. Okay, I get an output, so everything's good, and it's just a difference, so that works as well. So my MSE loss works, everything works. And now here I have to pass in an optimizer. I'm just going to be a class, well, let's just leave it like that. So self.opt is equal to opt, and I have everything. My forward input works. And now let's do the dreaded backpropagation. Define backward self, and it's just going define backward self, and it's going to get, well, the prediction and the target. So ytrue and ypred. And the first thing I'm going to do is calculate the loss. So I'm going to say MSE is equal to, okay, let's not assume anything. So I'm going to say loss is equal to self.loss dot forward, and it's going to take in ytrue and ypred. Now I have the gradient of the loss. So dloss is equal to self.loss dot backward ytrue and ypred. I'm not actually using loss. I'm just using it to print for printing purpose. I can say print fitting for loss equal to loss. So it looks like this. I have dloss, and now what I have to do is I have to go over each layer but in backwards order. So I have to say current delta is equal to dloss. And what I do now is I do for layer in reversed layers. I'm going to say current delta is equal to layer dot backward current delta. So this is literally just backpropagation. I'm going backwards and just going to populate everything with the gradients. So I did the backwards. And now what I'm left with is to, well, do the fitting. So I have to apply the optimizer. So define fit self x and, well, ytrue. And first what I'm going to do is I'm going to predict it. So I'm going to do self.forward x. So I have ypred is equal to self.forward x. And now I have to do backwards. So self.backward ytrue, ypred, and it's going to populate every single layer with its gradients. And now I can go over each layer and apply if it's possible. So what I can do is just for a layer in layers, and I'm going to put in a little flag. So if layer dot learnable is true, then I can apply the gradient. So I'm going to say layer dot apply, and I pass in the optimizer self dot opt, and it's going to automatically apply the gradients. So now I have to go over each layer and say whether it's learnable or not. So MSE loss I don't need to talk about because it's not even layers. I can just here I can just do learnable equal false. Here I can just pass in learnable equal false, and over here can do the same thing, but learnable equal true. So learnable equal true, and that's it. So now every single layer is going to have the gradients applied. You have the gradients calculated over here, and this is literally the whole backpropagation algorithm done. I modified the code to be more easily readable. So the first change I made was for backwards here, you see, I'm just going to remove the loss, and the return statement is just going to automatically just calculate the gradients and do nothing else. Then I have a function called apply, which will just go over each layer, and if they can be learnable or learned and contain the parameters, you're going to apply the gradients with that specific optimizer. And finally you have fit, which is just going to predict, calculate the loss, backward, apply, and that's it. And then I can return the loss, and we're done. So once you run this, no error. By the way, all the code will be on GitHub on the description, and feel free to join our Discord server, PokeCoders, if you have any question. It's kind of empty right now, but don't worry, with you here, you can make a difference. So x's, y's, looks like this. This is the XOR problem, which just means if you have 1 0 and 1 1, it's going to become an output of 1, but if you have 2 zeros or 2 1s, it's going to become an output of 0. XOR, which stands for exclusive OR. And this is my layer. It starts with a dense layer of 2 and then maps to 2 nodes. I pass in a ReLU activation to it, and then I have another dense layer that goes to 2 but to 1, and now I do a sigmoid activation. And I create this neural network and then go neural networks layers. I'd say it has an MXC loss, which is the loss, and then I pass in that the optimizer is go to SGD Optimizer 0.3. So once you run this, this has no errors. So let's try to make a little training loop, and first I'm just going to just predict our one sample with our totally dumb neural network because it didn't learn anything yet. So I can do NN.forward, and I pass in an input. So x is the first input of x is 0. And now you see I get an output. So this is amazing. So let's make our training loop. Let's just try something. If we just do nn.fit x is 0 and y is 0, if this works, this is going to be such an amazing, but I doubt it'll work first try. So let's try this. As you can see, it does not work. So I'll try to debug, and the first thing I have to do is dense layer object has no attribute learnable. So I guess I have no choice but to just pass it over here. So instead of just doing learnable like this, I have to do self.learnable is equal to true over here. I thought I could be lazy. And then for Sigmoid, I have to do the same thing. So where's ReLU? This is ReLU. I can pass in a self, then I have to put it below. And same thing for Sigmoid, sadly. So let's try this again. At least this is a minor bug. So run this, 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 and this, and this. So now I get another error. So let's see what the error is. So this time the error is apply takes 2 positional arguments but 3 were given. So this is a dumb mistake, I think, once again. And if I look at apply, layer.apply, it's going to look like this. So let's take a look at dense layer. And as you can see, apply just only accepts an optimizer, which is what I passed. So if I reread the message, perhaps I'm brain fart. Maybe I brain farted. Like, too much neural networks makes my brain explode. So let's look at the error again. Apply takes 2 positional arguments, but 3 were given. Okay, so it's my optimizer the problem. So for my optimizer, I have to go SGD Optimizer, and I have to look at their apply function. So where's my SGD Optimizer? It's over here. And here I forgot to put self here. Like, I'm such a little dummy. So if we put self over here, now this should work. So I run this cell, and now we can go back to the fitting process. So now if I fit, wait, I have to reinitialize. So now if I fit, bam, I get the loss. This is such an achievement. I think we might be onto something now. So the last thing to do now is just go over each samples and fit it. So for x, y, in zip x's, y's, I'm going to fit. So nn.fit x, y. And then I'm going to repeat that for I in range epochs. And I'm just going to do it like this, and that's it. So for I in range epochs for x, y, and zip x, y, I'm just fitting, well, x and y. So if I just do now, epochs is equal to 100, and I have loss is equal to 0, loss plus equal this, and then I just take the mean of that, so loss divide by the length, so x is dot shape 0, and I say print epoch I, and I pass in the loss, so the loss is this. Let's run at 4f, so 4 decimal points. And now if I close the square bracket like this, I get the loss. So is this diminishing? No, it's not. So let's try for a bit longer. Maybe it will work. So I'm going to put in 10,000, and here epoch I, what I'm going to do instead is I'm just going to do it at certain time steps only. So here I'm only going to print if I is a multiple of 1000. So let's try this now. And it seems that it's not learning. Update. I took quite a bit of time, I had to print a lot of stuff, but basically I found that my ReLU activation was messed up. So if I show only the Sigmoid activation, if I create a neural network with only Sigmoid activations, it looks like this. I fit, this is normal. And if I repeat the training, you see the loss goes down, and at the end just becomes kind of close to 0. So it means that it works really well. So if I want to show the output, what I can do is I can just do nn.forward, whatever thing I want. So I can just do for x, y in zip x's, y's, print target is equal to y, and I can say predicted is equal to y pred. And I'm just going to have y pred is equal to nn.forward x. And once you look at this, you see target is equal to 1, I predicted 0.98. Target equal to 0, predicted 0.01. Target equal to 1, predicted 0.98, and target equal to 0, predicted 0.01. So this is a neural network that works finally. I spent so much time on this, but now it works, and you can congratulate yourself, get yourself a pat on the back, because you just made a complete neural network from scratch, and you can adapt that to make pretty much whatever you would ever want to do. So now let's try to fix the ReLU activation function, because I will not tolerate my code not working. Alright, I figured out the bug. If I replace the ReLU activation function with this, it just looks like, you know, it's the same thing. It's just 1 times self.input bigger than 0. I found it on Stack Overflow. Thank you, Stack Overflow. But it still doesn't work. So the problem with this is just because my model is unstable when you're using ReLU. So if I run this many times, you'll see that's kind of weird. So if I run this again, see, this doesn't work. But if I wait for it to finish and I rerun this again, you see, now I get this. So now if I try to run this again, this still doesn't work. So I'm going to repeat that for many times, and you'll see one time it'll work. So it's just kind of where you start with. So ReLU works if you start at a good place. And basically, I did not implement weight initialization yet. There are many methods to initialize your weights properly, but I didn't do any of them. For example, one is called Zapier initialization, where you basically create the weights, but you divide them by the square root of the number of output nodes. But I didn't do that. So if I rerun it again, you see this starting point is good, because just by default, I get a very small loss. So if I run it again now, you see my total loss just becomes 0, and if I try it again, bam, I predicted perfectly without a hitch. So ReLU is just unstable, while if I use Sigmoid instead all the way, just because the way I created my weights, they work pretty well with Sigmoid. So if I do Sigmoid activation, and if I do Sigmoid activation over here, and I rerun it again, You see, no matter what, it seems like it's always working. So Sigmoid is much more stable than ReLU for my little toy model, but in practice you want to use ReLU because it works better. It's just because I did not do any weights initialization and do any specific tricks with the weights to make sure that they like land in the best starting place. So that's it. Thanks for watching. I hope you enjoyed this video. We just managed to create a whole neural network that you can extend to whatever you want with backpropagation, and you can add in as many losses, as many optimizers as you want, because this is a very extensive and modular code base. You can do pretty much everything you want. As I said before, code is on the description, GitHub, and join our Discord server to make our Discord server less lonely. So thank you, bye bye, and see you in another video.